When near the surface of a large body, there exists a gravitational field that will act to pull the object towards the center of that body. Gravity, right? The further from the center of the body an object is, the more potential for its height to be changed due to a gravitational force. If an object has height, it has gravitational potential energy. Does this ball have energy? No, it does not have energy, because in this situation, in this picture, the thing we care about is just the ball. There's no reference height, so it can't have any kind of potential energy. If an object has height, it has gravitational potential energy. There is no height if there is not a planet or something the ball is relative to in the picture, or the system. Remember, a system is just the piece that we care about, the parts that we care about. Without a surface, we would say this ball has no energy, it cannot do work, or have its energy transformed. Without something outside the picture, or something outside the system, or something external to the system acting on it. When we change our system, or the picture we care about, we add in the floor or the ground. Now the ball is above the surface, so now there is a height relative to the ground. So as the ball falls, there is going to be less and less gravitational potential energy because there is less and less height. As the ball moves upwards, we're increasing the amount of gravitational potential energy because there's a greater likelihood of the ball falling back towards the surface. The orange surface is the lowest point the ball will go, so we can say this is where the height equals 0. This is an arbitrary point, so we put it in the most convenient spot for us. This is allowed because height is relative to the 0 height. So when we're looking at gravitational potential energy, we can move this height equals 0 around. Normally we want to put that height equals 0 at the lowest part, or the lowest point that the system we care about is going to be going. Note, unless a problem or situation tells us about air resistance, we're assuming it's too small to change our measurements. In this case, we will also neglect air resistance. If an object has height, again, it has gravitational potential energy. Boom. Now it doesn't. In between, it had kinetic energy. Here's our equation for gravitational potential energy. U sub g equals m times g times delta y. Remember that delta y, we only care about a change in gravitational potential energy. If something stays the height the entire time, then there's no change in our height, no change in the y direction. That means there's no gravitational potential energy that we care about. Mass measured in kilograms again. G is our gravitational field, or acceleration due to gravity, measured as 9.8 meters per second, or 10 for easy calculations. Delta y is our change in height. Delta is final minus initial. There's our equation again. And looking at the units, we see a kilogram times a meter per second is a meter squared per second is the same thing as a meter squared per second squared, which is, of course, a joule. Work to us physicists means to change from one type of energy to another as a result of a force acting on the object. Some forces like gravity or springs can exert a force on an object and the energy is not dissipated out of the system. These are called conservative forces because they have a potential energy associated with them. A non-conservative force has no associated potential energy with it. However, some forces will do work and transform energy out of our system in the form of heat from friction, sound, and more. When this happens, we can call this work capital W for energy that is added or taken away from a system. The equation for work is work equals the parallel component of force times the displacement that has happened. Later in the unit, we'll go further into this, but for now we can calculate how much energy is dissipated or added using this F times d, and leave it at that. When a spring or some other object that has high elasticity is pushed or pulled by some force, elastic potential energy is stored within the object because the object will return to its original shape. As long as there's no spring compressing or expanding in our system, we will include elastic potential energy. Stretched spring, so we have elastic potential energy. Compressed spring that will go back to the size means we still have elastic potential energy. When a spring or some other object, as long as this spring is displaced from this rest point, which we call the equilibrium point, then there's going to be some sort of potential energy stored within that spring. Our equation is US equals 1/2 kx squared, where k is the spring constant, the springiness of the spring, measured in kilograms per second squared, and delta x is the compression or stretch distance from this equilibrium point, which is this yellow line. So that would be delta x on that end, and then as it compresses, there's delta x. Sorry, I know my face was in the way. Maybe I'll remember to change it. There's our delta x, and then back again. As long as there's a spring compressing or expanding in our system, we're using elastic potential energy. This block spring system is also moving, so we also have kinetic energy. So we would say our total mechanical energy equals our spring potential energy plus the kinetic energy it has when it's moving. Notice we don't have any height, so there's no gravitational potential energy here. Spring is vertical. Energy can always be accounted for. So total energy in the beginning equals total energy in the end. A conservative force, in this case spring and gravitational force, are doing work, or they're transforming all of that energy within the system. So there's no energy being lost to the environment here. It's a closed system. A closed system happens when there is no energy being added to the system or being taken away. When I add up all of our total mechanical energies, we have gravitational potential energy because there's a height. Then we have a spring potential energy, and we have a translational kinetic energy. And there's that rotational kinetic energy I hinted at earlier, but of course, we're not using it here. We can also use a trick to set our y equals 0 here, because this is going to be our lowest point the mass will go. So that's going to help us and allow for some of these variables to start canceling out. So it's a pretty useful trick. We can move this y equals 0 anywhere we want, as long as it's our lowest point that we go. And it's convenient to us. Spring up here at this instant, we'll just say we have 10 joules of spring potential energy and we have 20 joules of gravitational potential energy. Our total mechanical energy would equal 30 joules. Then as the mass moves down, now there's less gravitational potential energy and no spring potential energy, but the total energy still going to remain 30 joules. And then as it goes down even further, all of our gravitational potential energy is converted into the spring potential energy because there is no height. And this is the lowest we are going to go, and we said this is our y equals 0 point. So the kinetic energy is also not there because it's not moving, but yet our total mechanical energy still remains the same. At this instant, again, we have some gravitational potential energy, we have some kinetic energy, the total mechanical energy stays the same. And you hopefully start to see this pattern, that the energy can move around, but the total mechanical energy is going to stay the same. So when do we use this? If an object is deformed and it returns to its original shape, then there is elastic potential energy involved. When there's height and relatively low point, recognize that there is gravitational potential energy. If an object is moving or translating in the x or y axis, then there's kinetic energy. If any two of the above are true, we're going to use our conservation of energy. Conservation of energy is all of the stuff in the beginning equals all of the stuff in the end. Total mechanical energy in the beginning equals total mechanical energy in the end. In physics, we use subscripts. Here we use I and F. I stands for initial and F stands for final, but you can use whatever. So as I expand this and I try to account for all of my energies, I see I have kinetic energy in the beginning, gravitational potential energy, and elastic potential energy in the beginning. And then in the end, we have kinetic energy, gravitational potential energy, and spring potential energy, plus any energy that's been dissipated out of the system, which I'm using symbol W for work for right now. Then I can substitute all of my equations here. I know that kinetic energy is 1/2 mv squared, so I substitute that in. I know my gravitational potential energy is mg times y. I know my spring potential energy is 1/2 kx squared, and I do the same thing for the right side of the equation. And it looks like a big, scary mess, but it's not that bad because most of these are going to be equal to 0. So there's going to be a bunch of cancellation that's going to happen. So as we're going through problems, here's our problem-solving strategy for energy. Underline, highlight important information, draw it with important information in a dotted circle around the system or what you care about. Ask yourself, is there a height? Gravitational potential energy. Is there a spring? Elastic potential energy. Is it moving? Kinetic energy. To identify energy in the system. Is there any reason for energy to be lost? Is there any friction stealing some of that energy away? If so, then there's some dissipated energy. Work's being done to remove that energy. If there is more than one type of energy present, use conservation of energy, which says total energy in the beginning has to equal your total energy in the end, and then start doing your substituting of your equations. Let's look at a quick problem. An object of mass 10 kilograms starts from rest and is allowed to slide down a frictionless incline so the height changes by 10 meters. How fast is the object moving at the bottom of the incline? Remember our problem-solving strategy. Underline important information. So let's do it. There's important information. Mass. What else do we have? Rest. So that means our starting velocity is 0, so we have no kinetic energy because velocity and kinetic energy, there's a connection there. Frictionless, so there's no energy being lost. And a height change of 10 meters. So there's a gravitational potential energy change happening. How fast is the object moving at the bottom? If it's moving, it's got kinetic energy. If there's a height, it's got gravitational potential energy. If there's more than one energy, use conservation of energy. So let's draw it. Here's our object. We'll go with a gorilla. And there's all of our information, and we're looking for final velocity. As it slides down, how fast is it going? Total mechanical energy in the beginning. Remember, I said a lot of this is going to turn into zeros. No kinetic energy in the beginning because it's starting from rest. No spring potential energy because why would there be? And at the bottom, there's no gravitational potential energy and no elastic potential energy. So what we're left over with is our initial gravitational potential energy equals our kinetic energy. Plugging in our equations and solving for our final velocity, we get 10 times square root 2 meters per second.